Good evening, everyone. Um, I'm Professor Sean Tavalia, founding member of the board of the Hamptons Observatory and academic chair for physical sciences at Suffolk County Community College. On behalf of my fellow board members and colleagues at Suffolk County Community College, I would like to welcome everyone to tonight's presentation. For those of you who are unfamiliar with our organization, the Hamptons Observatory was founded 17 years ago with a mission to provide free, year-round, family-friendly educational events that focus on science and the natural world. Although the last 3 years placed a great deal of strain, to put it lightly, on a lot of non-for-profits and our entire educational system, they have also taught us how technology can be used to not only keep us connected, but provide access to education and ideas that none of us thought possible before. And tonight's presentation is a great example of just that. After the presentation, please visit the Hamptons Observatory website to learn about future presentations, join our email list, or donate to help ensure that we can continue providing these incredible opportunities. If you feel inspired by tonight's presentation, please visit Suffolk County Community College, where you can begin your journey into a scientific career at one of our 3 campuses in Brentwood, Selden, or Riverhead, New York, or from the comfort of your home through our online offerings. As we begin tonight's presentation, I ask that you keep your microphones muted. Please feel free to post questions in the chat at the conclusion of the presentation. We'll do our best to address all the questions. So without further ado, tonight's speaker is renowned for her pioneering work as a researcher at and co-founder of the SETI program. Many on the call may know her as the inspiration for Jodie Foster's character in the sci-fi movie Contact. Along with her work at SETI, Dr. Tarter has also worked on the high-resolution microwave survey, conducted numerous observational programs at radio observatories around the world. She was named one of Time's 100 most influential people in the world, one of the Time 25 in space, a recipient of the TED Prize, 2 public service awards from NASA. She was recently elected to the American Academy of Arts and Sciences, and even had an asteroid 74824 Tarter named in her honor. Please join me in welcoming Dr. Jill Tarter.
Well, good evening, everyone. It's really a great pleasure for me to be able to talk to you at the Hamptons Observatory about what I think could be this century's big game changer. And since you're astronomers, I can go through many of my slides without lengthy explanations, so there should be lots of time for questions. But by the time you leave here tonight, I hope that all of you, particularly the younger members of the audience, will think about yourselves in a way, and the way you interact with your world in a different way. Let's start by introducing me in a way that I would do it. So, okay, the slides were advancing, but now we have to come back down here. 3 screens is too much. It is just beyond me. Okay, let's see if we can get them to advance now. This was all working? This was all working? If I can, I'm going to stop sharing the screen and see if I can get back to where it's working.
Absolutely.
Frustration. Frustration. Okay, I'm stopping the share. Now we're going to go to
the fun part about Zoom is it made it all of us are our own technicians.
Yeah, right. Now I can't find the share button again.
Yep.
It's left the screen. Escape.
The good news is more people are joining.
Just see me putzing around. Oh, there it is. It went down there. So let's try there. And this is the screen I want to share. No, it isn't.
If I may interject, if you just share, there's share screen. There's a generalized share screen in the upper left of the various choices you have, if you are using PowerPoint, and then you can proceed just by clicking, using your mouse to click.
Yeah, I'm in the share screen and just trying to find the screen that I want to share with you. Because it isn't working correctly. All right.
Take your time, doctor. You're well worth waiting for.
Ah, you're very sweet. Thank you. Let's try this one. Share. No. You know what? I think I'm just going to go back to one screen and forget it.
We have it. It's there.
You're seeing that, okay?
We're seeing, who I am.
You can expand it.
Yeah.
Yeah, it's got to expand it.
That little. There you go.
All right. Now let's see if it will advance. Yeah. All right. So who am I? I work with a team that uses radio telescopes to try and find evidence of extraterrestrial technology. I'm the one that's not wearing the headphones. So name, degrees in engineering physics and astrophysics. My jobs have all been related to SETI ever since graduate school. And I was employee number 1 when we founded the SETI Institute in 1984. Here are some of the titles I've held. And I have an honorary degree from the University of Pennsylvania. And I'm nominally retired, but I call myself sort of the chief cheerleader for all things SETI. So before we can talk about finding them, I think it's necessary, perhaps not for this audience as much as some others, but let's try and put us into context. So where are we and when are we? Well, we're here, which in my case has been sitting around working from home for the last few years, like many of you. And that home is here in the Berkeley Hills, near the San Francisco Bay. Here and here, from the altitude of low Earth orbiting satellites, you'd see us here on the west coast of the United States. And of course, ever since Bill Anders took this picture in 1968, we've been able to actually begin to get a cosmic context for where we are. So this Earthrise picture is probably one of the most influential images that has ever been taken, because we see ourselves on one fragile ball in the blackness of space. And actually, a couple of years ago, if you got the memo, you went out on the lawn and looked up and waved, you could see yourself in this image here. The Cassini spacecraft looked back home and took an image of every one of us in that little dot at the end of the arrow. And we've long known, thanks to Carl Sagan's popularization, that we are a pale blue dot in an ocean of gas and dust. This is what we think the Milky Way would look like if we could get outside to take the picture. So this is what we think our galaxy looks like. It's actually a galaxy M101, but we think that the Milky Way is very similar to that. And again, we don't have any way of capturing that image in the optical. But if you use radio waves and you look at gases like carbon monoxide, you can actually map the galaxy from the inside out And you see, this is what we think for the past couple of years, using gas in our galaxy. This is what we think it actually maps to. So it's pretty close to M101. And of course, this is the famous Hubble Deep Field image. And we can see that each of these dots are not stars, but whole galaxies. And some of them are fainter and smaller, which reminds us that as we look farther away, we're actually looking further back in time. So we're now, which is the result of something like 3.8 billion years of cosmic evolution. And there are still problems with this image as we go back closer and closer to the beginning. We can't yet make gravity and cosmology play nicely together. So we struggle with dark matter, dark energy, gravity itself. It's really not possible to reconcile at this point quantum mechanics and gravity. But there are lots of very smart cosmologists working on that problem. So as humans, we trace our lineage not just back through the centuries of our families, and not just back through the millennia of human civilization with its art and its many experiments with different types of governance, and not just back over the millions of years since we branched off from the great apes, not just back the 2.4 billion years during which the Earth's atmosphere has been perfused with oxygen, thanks to the photosynthetic labors of blue-green algae or cyanobacteria, and not just back to the formation of the sun and our solar system 4.6 billion years ago. We have to go further back still to giant molecular clouds that were contaminated by the winds of Wolf-Rayet stars, or the debris from supernova explosions and radionuclides from neutron star collisions. The iron atoms in the hemoglobin molecules of your blood, the calcium in your bones and teeth, these elements were all fused, literally cooked up deep within old massive stars that ended their lives in catastrophic explosions. We call them supernovas. They blasted off the outer layers of the star, leaving behind remnants like this modern example. Remnants that became incorporated into our solar system, just as this supernova remnant will be incorporated into future generations of stars and planets, and perhaps life. So one thing that we've learned from 400 years of astronomical study is that it does take a cosmos to make a human. And we've begun a new branch of science called astrobiology. And underneath the umbrella of astrobiology, there are researchers looking for biosignatures, and then my colleagues who are looking for technosignatures. So the trick here is to try and find inhabited worlds because of the actions of their inhabitants. And so when you're talking about life beyond Earth, you can discover it either in situ by finding biomarkers on the places that you can actually physically go to. You could perhaps discover artifacts within our own solar system, as the controversy about Oumuamua has indicated, that this is a body that came from outside the solar system into the solar system, and some like Avi Loeb have argued that it's a piece of technology. Or you could look remotely for biosignatures in the atmospheres of exoplanets orbiting nearby stars. So when you look at the atmospheres of Venus and Earth and Mars, you find that their spectral signatures are quite different. The Earth is very different than any of the other planets. right? And we have in our atmosphere non-equilibrium chemistry. We have oxygen and methane coexisting in the atmosphere, and they really shouldn't, because these are very reactive gases, and if you put them together in the laboratory, they turn into water and carbon dioxide, and that's happening all the time in our atmosphere. But because of biology on the surface of the planet, which is replenishing the oxygen and the methane, we find this non-equilibrium chemistry. And of course, that's what we'd like to be able to look for in the atmospheres of distant exoplanets. And there's a lot of research going on now in the astrobiology community to understand what might be the best candidates for biosignatures and how to interpret them and how to recognize false positives. There's a great deal yet to be known. And at the moment, I would say that we don't yet have a smoking gun, but a lot of clever people are working on it. Recently, we had what turned out to be another false positive, right? There was the suggestion that phosphine had been detected in the atmosphere of Venus in the cloud layers. And this would be really exciting because on Earth, whenever we manufacture phosphine, it always includes some biological process. So did this mean that there was biology in the clouds of Venus? There was a lot of excitement for a while about this idea, but then actually it looks like it's SO2, not phosphine. It was really only a single line detection and was not definitive. So this looks like a false positive that we can put behind us. But what about Enceladus, right? We are planning missions to go fly through the plumes in the south pole of Enceladus to see if perhaps there might be, if not biology, the building blocks of biomolecules in those plumes, because those plumes are accessing the liquid ocean under the surface of that outer icy crust, and in fact also exploring the inner core. And so we need to figure out how to collect this material, how to amplify it so that we can actually make measurements on it, and how to deal with any ambiguities, right? This isn't going to be an easy measurement. It's going to take a while, and there will probably be surprises. And how do we deal with the ambiguity? Well, I'd like to suggest that ambiguity could possibly be reduced if we decide to look for mathematicians rather than microbes, right? So that's what SETI is all about. We want to detect the work product of life, either technosignatures or perhaps some kind of vast astroengineering projects that we hadn't expected that might surprise us. So technosignatures, there can be two kinds of deliberate signals if someone is trying to attract our attention, right? They can be almost natural, or they can be obviously engineered. Now, the thing about almost natural is that as we do our astronomy and astrophysics and build tools to explore the universe, we'll capture some of these things in our databases. So here's a pulsar, right? A very accurate clock. And we've had pulsars that we've observed that have changed their period. But we've never had a pulsar that went from a first period to a second period and then back to the first, right? But they could be in our databases. And we should be keeping our eyes out for this sort of almost natural signal. Another example of an almost natural signal would be an artificial eclipse. So we're told by the IAU that planets by definition are round, and therefore their shadows on their star in transit will be round. Well, planets are spherical and their shadows will be round. But what about artificial bodies put in orbit around their star in ways that would signify a non-natural shape? So a Venetian blind or a triangle or a flag of some kind, which in the ingress and egress phases of the light curve will have higher moments that will distinguish the transiting object from a sphere. Okay, and how about this? We take a Cepheid variable, right? And we build some sort of big energetic neutrino factory or something, and we orbit it around a Cepheid variable. And we notice that the Cepheid period is very precise, but we use this big energy source so that as the star has collapsed and relaxed and is thinking about expanding again and getting brighter, we zap it with some energy source and we cause it to expand prematurely. Now we have just, developed two periods for this Cepheid, the natural longer period and the shortened premature expansion period. So what you've got is you've got a Morse code of long and short. And that Morse code is strong enough to be seen all the way to the Virgo cluster. It's a very, very bright source. And so we could, in fact, slowly communicate information this way over a very large distance. So those are just some of the things that I've been thinking about in terms of almost natural signals and what new telescopes may be able to provide us with. In terms of the obviously engineered, well, since the 60s, we've been looking for a single frequency on the radio dial, a narrow band radio signal. Then we added optical, very short optical pulses to the search. Again, sort of thing that we don't think nature can do. And more recently, we've been talking about monochromatic lasers that might be powering starships. So clearly things that nature doesn't do. And the difference between these categories, the reason I separate them is because for the almost natural, the observational consequences is that you just do astronomy in any way you can think of, and particularly new ways of opening up the phase space to observation and see what's there. But the astronomers are not going to be building tools that are likely well suited to finding these obviously engineered choice signals. And so you need to conduct very systematic searches for this particular kind of thing. And you need to build dedicated telescopes in order to succeed. So SETI has been part of NASA since the mid-70s and up through congressional termination in October 12th of 1993. So workshops at NASA Ames, that's what NASA always does when it wants to start up some sort of new exploratory science. You hold a bunch of workshops, and out of these workshops on SETI actually came working groups on how would you find exoplanets, because at the time we didn't know whether any other stars had planets. And so exoplanets was one of the outputs from those workshops. A book called SP419, where we wrote up all the kinds of ideas. We won Proxmire's Golden Fleece Award twice. We actually began what was to be a 10-year project called the High Resolution Microwave Survey on October 12th of 1992. And then Senator Bryan shut it down and terminated it in October 12th of 1993. And so we decided that, you know, this federal funding was not very reliable, and we would have to go out and raise private funds to keep SETI going. And so we started in 1994, we started Project Phoenix, which is rising from the ashes of congressional termination. Why not be dramatic about it while you're at it? So we held another series of workshops, and we wrote up the results in a book called SETI 2020. We decided to expand the wavelength coverage into optical and infrared, to build dedicated telescope that worked 24/7 so that we would have sun sensitivity to transient signals, and then look at all the sky all the time for constant or transient signals. And here's one of the telescopes that we've built. It's the Allen Telescope Array in Northern California near Mount Lassen. So it was supposed to have 350 6-meter telescopes. However, there was a lot of technology development that we hadn't yet done. And by the time we finished it and knew how to build these things, we only had enough funding for far fewer telescopes. And if you're going to stop short of 350, I couldn't think of any number better than 42, the answer to life, universe, and everything. So we have 42 and stand ready to expand them when funding becomes available. But we use these every day as an interferometer. They have a unique, very, very wideband receiver system. They cover all frequencies from 1 to 10 gigahertz simultaneously. Most wideband receivers have a factor of 2, maybe 3 in terms of the frequency coverage. The dishes are 6.2 meters because they're made in Idaho Falls, Idaho, and they don't do metric in Idaho Falls. So these are 20-meter dishes. And the field of view is very wide because these antennas are small. So we have huge field of view. And because it's an interferometer and the telescopes are widely spaced, we also have very good spatial resolution on the sky. So to give you an example, what that means when you're looking at the sky, here's the Andromeda Galaxy. All right, here's another object, familiar object for scale. That's 0.5 degree across. The Andromeda Galaxy is 2.5 degrees across. Until, sadly, recently, we had the Arecibo telescope as our largest telescope. Because it was so large, its field of view on the sky was very small. Even when we made a focal plane instrument that was multi-beam, the 7-beam instrument, still you couldn't cover much of the sky at one time. But a 6-meter telescope, 20-foot telescope, has a very large field of view. And because there are many telescopes spaced widely apart, you can also make a radio camera with something like 1250 pixels and 1024 colors or frequency channels. So it's a really good survey instrument. It's a wide angle radio camera that can work in a snapshot mode. You don't have to use aperture synthesis because there are so many baselines that you can take short observations and make images. It also has beamformers. And so you can focus the entire collecting area onto individual small beams and phase them up with all, and in our case, we can do 2 frequency beams, 2 frequency tunings at once on 3 beams, and that can grow in the future. In fact, it will, with a project called Cosmic that's going to be built on the Very Large Array. So, and there's one more trick that you can do with an interferometer. That is, you can null. You can actively null regions on the sky. So you can keep interferers from ever getting into your data. You can track satellites with these nulling beams and keep them out of your receivers. So we began in 2007 to observe with this telescope, and we used a catalog called HabCat of target stars that we thought were likely to host planets. We didn't know, but we thought it was a good idea based on the stellar properties. And then, of course, once Kepler began delivering us these fantastic yield of exoplanets, we then knew that now almost every star is going to have at least one exoplanet. And so what we do now is we've been working on the 20,000 closest stars to the sun, almost all of which are red dwarfs. So you can see in this two-dimensional diagram of declination and right ascension of what we've looked at least until this was 2017 when I made this plot. You can see where we concentrated on the Kepler field. And you can also see a big blank strip where we haven't observed anything, because that down in the south is looking into the geosynchronous belt. And if you looked there, those transmitters are so strong that in some cases they can in fact blow out the receivers. And so we put Schottky diodes to clamp down on any unfortunately strong source that we come across. So that's what we've been doing at the SETI Institute. But the newest game in town is Breakthrough Listen, where Yuri Milner pledged $100 million over 10 years to fund SETI research. And so it's been going on at the Green Bank 100-meter telescope in West Virginia, the National Radio Astronomy Observatory, and in Parkes, 60-meter dish, New South Wales, Australia, at the optical telescope in right down in this is the planet finding telescope down the road at Lick Observatory, and will be going on to, or has already gone on to, these other dishes in China, the FAST telescope, the Meerkat telescope in South Africa, and Jodrell Bank in Maryland in the UK. So there's more SETI on telescopes today. There's SETI at Home, which had run for decades. It was really the first citizen science project that we engaged the community, the world with. And I think it put citizen science on the map because SETI was such a sexy topic. We were running the 7-beam detectors at Arecibo until sadly we lost Arecibo, and SETI at Home has so much stored data that they're not taking any new data. LOFAR in the Netherlands and Sweden has done SETI work. There's a group in Italy with a SETI Italia. There is a group down at JPL. Now, when NASA started SETI, it was two centers that were working on it, NASA Ames in the north and JPL in the south. But when this NASA project got terminated, JPL's scientists had to back off. They weren't able to continue. But now they have taken one of the, I think it's 20, I can't remember, 25-meter telescopes out from within the NASA boundary and put it outside and begun an educational project that they call the Goldstone Apple Valley Radio Telescope. And that is run by local students and teachers. And so now, and some of the JPL scientists who began SETI sky surveys are volunteering and helping the students to do a sky survey with this Apple Valley telescope. Well, okay. It doesn't seem to want to move on. Okay, there. Okay, it finally came up. And there's a gentleman in Japan who organizes occasional observing campaigns where he gets telescopes from all different countries to work collaboratively, observing in different ways the same piece of sky. And what's coming up now, which would be on the air now, save COVID, is a new back end for the Very Large Array. And the Very Large Array operates with what they call a wide arc correlator to make images of the sky. But that correlator is so old and so non-digital that they're actually afraid to turn it off for fear that they won't be able to get it back turned on. And so what's going to happen is that Andrew Simeon who's from UC Berkeley SETI Group and the SETI Institute, is building a new back end for that, the VLA, in which the output of those 27 antennas will go into a new digital signal processor to look for SETI. But in the process, Andrew and the team will be teaching the VLA how to build their own new digital correlator. So it will in fact upgrade that instrument. And this processors will be looking for, in our case, the SETI Institute's case, will be looking for artificial signals. Optical SETI got started quite a few years ago at Harvard. And if any of you know Andrew Howard, you might recognize his younger self there with the telescope that he built at Harvard to do an optical sky survey. The data from the Keck high resolution spectrometer also gets reanalyzed looking for artificial signals. There's in Panama, there's a private optical SETI site called the Buquete Optical SETI Observatory. We actually look at archival data too, data taken by the WISE telescope, for example, that looked over the entire sky, and that's been reanalyzed by students looking for Kardashev type 2 or Kardashev type 3, very bright civilizations. And there are new optical SETI projects getting underway, right? The first one to be on the telescope is Veritas, the Veritas array, and they have at the focal plane of each of those 4 telescopes, they have photodiodes, about 900 photodiodes. And so what's been happening is that normally when these telescopes are looking for showers, for air showers, they require that many pixels in a row light up across the focal plane. But we were able to collaborate with them and write some new software that now looks at single pixel events and requires that it's the same pixel on the sky that lights up in all 4 telescopes as a potential for a trigger for a technosignature. Shelley Wright is running a group down in UC San Diego to build PanoSETI. It's essentially a geodesic dome that has these large lenses in them, in each of the dome spaces, and it focuses 10,000 square degrees of the sky on very modern sensitive detectors. And then at the SETI Institute, we're building something called Laser SETI. The idea here is if we can build enough of these, like 15 locations around the globe, we can be looking at all the sky all the time in the optical region for transient signals. JWST, right? Well, it's launched and it is certainly looking at exoplanet atmospheres, finding some amazing kinds of things. It's looking at transmission spectra for hot Jupiters, and it's looking to see if some of the scientists are looking to see if they might detect technological pollution in the atmospheres of those hot Jupiters, such as CF4 or CC13F. We have HABEX, which is now the Nancy Grace Roman telescope. And we're talking about a telescope that might be actually capable of detecting life and not just evidence of biosignatures and biomolecules. So something called the Large Ultraviolet Optical Infrared Telescope, for a really dull name, may in fact be large enough to be able to detect evidence of biosignatures around nearby exoplanets. Here's something I bet none of you have ever even thought of a optical telescope that might look like this. It certainly looks more like a radio telescope. It's an interferometer of sorts, and it should be able for Proxima b and only Proxima b. It should be able to see and map the difference between continents and oceans and do some spectroscopic work. If this ever gets built, we're not good as astronomers often at building single purpose instruments, and it's not clear that the community will have an appetite for something that can only do one thing, although that would be pretty spectacular if it were built. The TMT, the 30-meter telescope, the giant the GMT, the extremely large European telescope at something like 40 meters, I think downsized from an initial wish list of 100 meters. The large synoptic space telescope, which will give us an image of the sky every 4 days and give us some sensitivity to transient phenomena. Laser SETI, I've already mentioned, Pano SETI, Veritas, and then the Chinese with their large radio telescope, larger than Arecibo, it's 500 meters across, are doing SETI observations with FAST. And in the future, the square kilometer array will be used to make SETI observations in a commensal fashion. That is, there will be a primary observer who has the ability to point the telescope and choose the frequency, but SETI can use the telescope commensally, eating out of the same dish at the same time. Hopefully we'll get the next generation VLA, and that will also do SETI. And if that extremely large telescope could ever be built and get made to work as an optical interferometer, there's something called Colossus, which would be 70 meters across, an expansion of that kind of interferometer, and in fact would be able to detect the heat islands of any cities on nearby exoplanets. Square kilometer array coming on board day after tomorrow. Maybe not just 3 phased beams, but 250, and they will be able to probe millions of stars identified by the Gaia catalog. So that will be the first time, the square kilometer array, when we have enough sensitivity to be able to detect leakage radiation such as we generate on the planet light years away. And some things never change. This is the flag of Earth that was designed by James Cadle in Iowa when NASA was going to the moon for the first time, and he thought that this is the flag that should be flown on the moon rather than the flag of the US. Of course, you know what happened. We didn't, but where we are observing with SETI, we fly this flag and we still plan for success. It's getting harder as the sky gets noisier from all of our own technologies. Here you can see the frequency band from 1 to 3 gigahertz as it got filled in with our own technological interference between 1995 and 2004. And you can see that the Allen telescope array, which covers far more frequencies, is also having to contend with this kind of interference, although it is relatively quiet at Hack Creek Observatory still at the moment. So the technologies for the search have changed dramatically. We started with full custom chips. We had to make our own Fourier transform chips to do this fast enough. And now the new backends being done by UC Berkeley and the SETI Institute based on GPUs. So over 50 years, we've been doing SETI. And when SETI turned 50, I said, okay, there's 9 dimensions of phase space in which a signal might be detectable. And how much have we changed? How much have we searched of that phase space? Well, when SETI was 50, I calculated it was a part in 10 to the 23 of the world's oceans. I said, let's make the world's oceans the phase space that we need to explore. And how much have we done? Well, it was a glass of water out of the oceans. Jason Wright's students redid the calculation a couple of years ago, and it was more like a small swimming pool's worth. But there's still a lot to explore. And this isn't just Moore's law. We're doing more and faster, but it's because there are parallel improvements that can be made in the exploration. So dedicated telescopes, more wavelengths, more time on the sky by using commensal opportunities, and improved algorithms using machine learning for doing the searches. So the last thing about life beyond Earth is we could export it. We could take it off Earth. Moon, Mars, the asteroid, breakthrough starshot, the 100-year Starship study, Icarus. We may be going there. And I like to talk to audiences about SETI because I think that thinking about life elsewhere has the effect of holding up a mirror and seeing ourselves in the mirror and thinking, well, we all look different, but coming to understand that no, in fact, we are all the same. We are all Earthlings. And I think that's the cosmic perspective that is going to be so important for solving the challenges that we face on this planet. So it's not just me. Caleb Scharf, the director of the astrobiology department at Columbia, has said, on a finite world, a cosmic perspective isn't a luxury, it's a necessity. So you now have a homework assignment. When I stop talking, go take all those devices that have profiles about yourself on them and change those profiles so that the first thing that you say about yourself is that you're an Earthling, and then start acting like it, because I think that's what this planet needs. Thank you.
Thank you, Dr. Tarter. That was wonderful. And a chilling way to end, too.
Well, yeah. This is my hobby horse now.
So there are,
perspective.
Yeah, there are a couple of questions in the chat. First one from Lydia Maria says, what do you, wonderful talk first. What do you say to those astronomers who believe we may be a simulation?
Well, I don't say anything because I don't have the expertise that's necessary to evaluate that claim. And, you know, I want to tell you about science. If I start talking about belief, then that's religion and not science. So I can't address, with my skills, I can't address the simulation problem. But, you know, folks at Oxford and the Center for the Future of Humanity, those kind of folks are thinking about it seriously.
Next question is from William, and he says, what are the prospects for building a SETI radio telescope on the far side of the moon to block human-generated radio signals?
Yes, we've been talking about that for a very long time. We've even identified a particular crater that we'd like to use. But guess what? Guess what's going to be orbiting directly over that crater is NASA's new space station, right? So we're talking with the frequency managers and trying to make the case that whatever communication systems they put on that, they should do so utilizing two different frequencies so that at some time we'll be able to look through the entire spectrum, right? Not all the time, but if you alternate between those two frequencies, then we will have access to the spectrum. I don't know. It's not going to happen in my time, but hopefully it will happen.
Natalie asks, any thoughts around Congress's UAP reports and implications to studies of alien life and technologies?
Yes, there are some really good websites, and I will send it to you and you can distribute it because I can't do it right now, given my three screens are once again messing up. That note that there are explanations for those phenomena, and they often are recorded in newly turned on and commissioned instrumentation. So the best explanations are often that we don't actually completely understand how this instrument works.
Julia would like to know, why don't we send bait out and let them find us?
Well, we've sort of been doing that. We started transmitting, early on, and there is now a bubble, a radio bubble that's 80 to 100 light years in radius, and that's very detectable. These are obviously engineered signals that we've been transmitting, and some people are extremely upset about this, right? Because they're afraid that we will be detected and then they will come and, I don't know, eat us for lunch or use us for slaves. But the point is that horse is already out of the barn. And I think that it's not likely that we're going to talk or convince the rest of the world's technologists to turn off all their toys and to stop using airport radars and all the other things that we use and satellites for communications purposes. We're really hooked on our digital and radio communications devices. So that's the reality.
So Lydia would like to know, are there still opportunities for amateur astronomers to participate in SETI research?
Yes. Send me an email and I'll put you in touch with the programs that are going on.
Lydia, I can provide that information for you in the chat in just a few minutes. Julie, also, did we follow Umaguma back to its origin or its course after visiting us?
Only to the extent that we know that its origin is outside the solar system, right? There's no unique solution to the observations that says it had to start here. It just had to be on this track coming in from outside the solar system. So no, I'm not aware of anybody who's tried. I don't think it's actually possible to trace it back to its actual origin.
Stephen wrote, since Newton ushered in the Enlightenment, what changed in the intellectual landscape once actual life is discovered?
Well, I think the changes in the landscape over these hundreds of years have been, extremophiles and exoplanets. Yeah. Neither were expected, and they are both just busting over, and they're really productive fields. And the thing that I like about them, being very personal here, is the fact that because they aren't old, academic, tried and true, siloed disciplines, that there's plenty of room for young people. And I think some of the best and the brightest that are popping up in these fields are young women. And so I really applaud that opportunity. But yeah, extremophiles and exoplanets, and who knows what the next unknown is going to be when we turn on all these different telescopes.
So this is a great question from Brian, who wants to know, what's your best guess as to the time it will take to contact extraterrestrial life?
Depends on how far away it is, right? We've got the tyranny of light speed. We can't go any faster than that. And so if it's 4 light years away, well, then it's 4 years. But if it's 1,500 light years away, then that's a lot longer, right? And we have to, I think, rethink our concept of communication. So when we say communication, we tend to be biased and be thinking about two-way communication. So I'm talking to you, you're asking me questions, that kind of thing. But I think when we talk in these terms, we might better think about Shakespeare and the ancient Greeks and Romans, who have transmitted information to us over centuries, but it's a one-way communication. We get to learn a lot about what their lives were like, but we don't necessarily have the opportunity to ask questions in return.
I guess we're going to ask a follow-up to that, which is from my own question. Do you ever get disappointed that we haven't found anything yet?
No. Remember the ocean and the one glass? No, nobody goes into this field if they don't appreciate exactly how big and vast this search is. And so I don't get disappointed because I think perhaps someone in the future will make a discovery. But the thing that excuse me, that's my dryer. The thing that I focus on is the fact that I try to do something this week that will make the search better than it was last week. And if you get satisfaction out of that sort of progress, then it's a good thing. It's a really wonderful thing to work on. We've been asking this question for forever.
Carlos has a question. Yes, is it reasonably possible for us to be reached since galaxies are so far apart and are getting more distance, and their technology would need to be much quicker?
Or older.
Or older.
And, I mean, that's the other thing that I think is important about SETI. Yes, we can't even get to the nearest star with the technology that we have now. And of course, our galaxy is 100,000 light years across, and we can't begin to think about how to span those distances. We think that perhaps within the galaxy, as stars are moving relative to one another, a distant star may come close to us and give us an opportunity to reach it. But the thing that I think about is if somebody could get here, then their technology is more advanced than ours. Probably means they're older than we are, probably by a lot. And for me, that's hopeful in the sense that we find ourselves in a technological adolescence, and we don't know whether there's a long future for us. But if somebody else can get here, it means that they managed to get through that bottleneck that we seem to be occupying at the moment. They made it through, so we can too.
Lee Davis asks that he heard that the James Webb telescope was damaged. Can you elaborate?
No, I can't.
Yeah.
I know that during construction, there was some damage that was repaired, but I'm not aware of any. If he's talking about recent damage, I'm not on that grapevine. And I have someone who's working with my husband here, and now I have to leave and go help them. But
okay. Thanks
for the opportunity to talk with you this afternoon. Thanks for the questions.
We really appreciate your time, Dr. Tarter. Thank you.
Okay. Bye-bye. And maybe we'll get on top of the Zoom stuff eventually. Okay.
Have a good night.
Bye-bye.
Thank you. Good night, everyone.
Karen, if you just hold on 1 second, I'll get that for you. I hope everybody enjoyed the talk, and I hope to see you guys again at another event in the future. Thank you.
may